Hello, this is John Clark, and I'm going to go through Assignment 0902, the game of life. Let's start out by running the program with a few variations. Okay, we can see that I have a p-value of 0.1, size of 20, and a t of 10. Let's try that again. Okay, something looks kind of similar. All right, let's try changing the probability to 0.03. Let's say S is 40 and T is 30. Okay, sort of dying out there, it looks like. Let's try that again. Oh, we only got 2 left there. Let's do T of 50. Oh, there we got a bunch. Okay. It just all depends on which iteration. Okay, let me try now finally a higher number for probability. We'll say 0.9. And there we can see the board is empty, and I can run this pretty consistently. And it's going to give me an empty board. If I bump it back to like 0.7, you know, there's some there. Okay, so let's go ahead on into the code and answer the questions. Creating an array involves one statement which uses NP random choice. First, I create a single flat array with 1 and 0 as the two options, the size being s times s, and the probabilities of the respective values being p and p minus 1. Then I reshape that to be a two-dimensional array. As far as the logic goes for updating the board, going to the advanced function, it accepts two things, b, which is the current board, and t, which is the number of generations. I start out by determining the value of s and making a copy of the board so I don't disturb the original. Then I've got a nested for loop. The operations all work on what I call a supercell, which is the current cell and the 8 surrounding it. I define the value of the start row, end row, start column, and end column using the concept where I can wrap around to the other side. Then I go through the array square by square, adding the values of those 9 numbers. I tried to come up with a way to make that addition more elegant, but this seemed to be the best way I could come up with the way the things wrap around. After that, there is some logic to implement the Conway rules. I tried to make it more efficient because we've got an n cubed algorithm here. The biggest thing I did is that I only touch the board if the conditions exist that cause a change of the state. I'm sure there's other ways to optimize it, but that's what I came up with. The final question is which values of S and P did I find create an interesting colony of cells? I found that small values of S, the board sometimes seem to empty out more frequently due to overpopulation. The larger the board, the more space there seemed to be for the colony of dots to grow. Outside of that, with a lower or higher value of P, the colony also tended to die out, either due to overpopulation or underpopulation. There seemed to be a sweet spot in the middle where things grew most comfortably. The inflection point, for example, on the high side seemed to be somewhere around 0.7, where things tended to die out. Another thing I found running this a bunch of times is it honestly seemed kind of unpredictable. I expected it to be more deterministic. And I'd run it with the same time with the same, or multiple times with the same parameters, and it would end up with a different result. So that's it. End of video.